In this video, we will learn the basics of dimensional analysis, which is a tool that we use to approach a problem in a new physical system. Supposing we want to look at a mass attached to a spring. So we have mass m attached to a spring of spring constant k, the other end of the spring is attached to a wall, and it's oscillating back and forth on a frictionless horizontal surface. And we want to know how the time period of oscillation depends on the mass, the spring constant, and the amplitude. So the main question is, what is an expression for the time period t? And we're just trying to guess what all it could depend on. So one parameter is obviously the mass, another parameter is the spring constant, and we might imagine, oh, maybe it depends on how much I stretch it as well. Maybe it will take longer if I stretch it more. So how do we figure out the value for t? Of course, we could set up the equation of motion and then solve it, but dimensional analysis gives us a kind of shortcut. What we do is look at the dimensions of each of the quantities. So, for example, mass has units of kilograms, but we'll just say it has dimensions of mass. Time period t, which we want to find, has units of seconds, with dimensions of time. Amplitude a has units of meters, but again, we'll be working with the dimensions, which are dimensions of length. And the spring constant, k, is in newtons per meter, but we will simplify it to dimensions of mass over time squared. So dimensions of mass and then dimensions of time to the -2. So what we say is we make a guess that the time period is going to depend on the spring constant to some power a times the mass to some power b times the amplitude to some power c. Now we plug in the expressions for the dimensions. So time period has dimensions of time, no surprise there. The spring constant is mass and time to the -2. You raise the whole thing to a. Mass is just mass, amplitude is a length, and we have the respective powers. But the dimensions on both sides need to match up. In other words, units need to match up. So on the left-hand side, we have mass to the 0, length to the 0, time to the 1. And on this side, we have mass to the a plus b, time to the -2a, length to the power c. And so, comparing, we have three equations. We have 0 equals a plus b, we have 0 equals c, right? Powers of length on both sides should match, and powers of time on both sides should match. So we have 1 equals -2a, and we can solve this. So c is equal to 0, that's fine. A is equal to -1/2, and then plugging that in over here, we see that b is equal to +1/2. And so putting this all together, what we find is that the time period is proportional to the square root of the mass over the spring constant. Right. So notice that just by doing dimensional analysis, we have shown that the time period will not depend on the amplitude for this system. Now there is a caveat. Notice that all we got was proportionality. So this method of dimensional analysis works for quantities that have units, but it can't really say anything about quantities that don't have units. So dimensional analysis does not pick up on pure numbers and functions that give you pure numbers like trigonometric functions or exponentials. It won't pick up on those. Right? So stuff that depends on angles, if the angle is measured in radians, radians is really a unitless or dimensionless unit. so it will not show up properly in the formulas. In this case, we found that the time period was proportional to the square root of m over k, but it's not equal to the square root of m over k. In fact, it is missing a factor of 2 pi. So dimension analysis has its limits. It can't find everything. But if you just want to figure out the power dependencies, then yes, it can tell you, oh, it's proportional to m to the 1/2 and k to the negative 1/2, like so. Let's continue with one more example. So we can ask, if we have a string and we send a pulse down the string, we can ask what is the speed of the wave of that pulse on the string, and what does it depend on? So, well, we look at the properties of the string. We can measure its mass, we can look at its length, and another property is we can imagine that, oh, maybe it depends on the force of tension in the string. So again, we do the same thing. We look at the dimensions of all the various quantities. So we have mass as dimensions of mass, length as dimensions of length, force of tension, which is units of Newton. Convert that into dimensions. We know a Newton is kilograms times meters per second squared. So that would be mass times length times time to the negative 2. Right. Then finally, we want the speed of the wave, which is meters per second, which is length times time to the negative 1. So we then give our best guess for how the velocity depends on these factors. So we have the speed is proportional to mass to the power a, length to the power b, force of tension to the power c, and we compare the dimensions on both sides. So on the left hand side we have length times time to the negative 1. On the right hand side we have m to the a, l to the b, and then this combination to the power c, and we simplify. Alright, and now we can compare the powers on both sides. So if we compare the powers of mass on both sides, we see that 0 is equal to a plus c. Powers of length on both sides, we have 1 is equal to b plus c. Power of time on both sides, we have negative 1 equals negative 2c. Alright, so we start from here, we solve for c. C is equal to 1/2. Take that over here, then b is equal to 1/2. And then take that over here, and we have a is equal to negative 1/2. So putting that all together, we find that the speed of the wave on the string will be proportional to the square root of force of tension times the length of the string divided by the mass of the string. You might see this written as the speed is proportional to the force of tension divided by, you will see it either written as mu or lambda, but basically, so if we call it mu in this case is m over l, it is the mass per unit length of the string.